Welcome back. Well, good to see you again. I mean, I don't see you, you see me, but okay, that's the same. So now we know how charged particles interact with matter. Now we're going to some more intricate questions, right? Because we said that charged particles they interact with matter via direct Coulomb force, right? But then photons they do not have charge. So how do they interact with matter? It's not simple collision as happens, or simply radiation, right? In fact, photons interact with matter essentially by indirect means. The most important ways are pointed out here. So there's Rayleigh scattering. Rayleigh scattering is when the photon has very, very little energy and it will scatter with the atom as a whole. It will lose very, very little energy in doing that, or no energy at all. And so this is not important to the understanding of the processes we are trying to show here. This is also called coherent scattering, right? But it's not interesting for what we're doing here. Then there's these three ones here in bolder font: the photoelectric effect, the quantum scattering, and pair production. And finally we have photonuclear reactions, which we have talked a bit about in nuclear reactions. They are just like other nuclear reactions, so they are not relevant to this class. So in this class we'll talk mainly about these three effects here, right? Because photonuclear reactions are much less likely, and Rayleigh scattering, although it's very likely, it has very little effect on either the radiation or the target, right? There's other effects too, like for instance X-ray diffraction or something, but in all these cases you do not damage the target and you deposit very little energy on the target. You don't shield radiation using it, so they are not useful for these kinds of things. If you want to know more about it, we can talk about it later, right? There's a lot to say, but it's not really important for this class. We do not have the time to take all these questions. So let's go to what really, one way or the other, make difference in the shielding the radiation or in damaging the target. So the photoelectric effect is the most simple to understand. The gamma ray or X-ray comes here. It gives all its energy to one single electron, and this electron is ejected from the atom. Right? For energy conservation, it's easy to see that this electron will have the initial energy of the photon less the binding energy of that electron, right? So okay, and of course after it happens you either have X-rays because the other electrons entered here, or Auger electrons, which is something that competes with X-rays. It's essentially, instead of emitting an X-ray, the atom emits an electron which takes away the excess energy, and then it's left ionized. But okay, the important thing here is the photon puts all of its energy on a single electron. So these electrons have a very well-defined energy, right? It's not an energy range, it's a very well-defined energy, right? And the cross-section for photoelectric effect, it goes to the atomic number, with the atomic number to the fifth, and the energy to -2 or something, almost that. So it's much larger, much larger for heavier targets, and it also decays with energy, meaning that if we take a look, this is take note that we are on a logarithmic scale, right? So for z equal, I don't know, 30 at 500 keV, you have something like 500 barns. I don't know the scale here, should be millibarns or something. If we go to Z equal 90, which is essentially, now we're talking about uranium, it's more than 10, 100, it's more than 200 times larger. So you can already see that photoelectric effect predominates with higher Z and lower energy, right? Then there's Compton scattering. Compton scattering is almost the same idea, but now the photon comes, it deposits part of its energy on one electron, and you have a scattered photon is emitted. We call it scattered by habit, but it's a second photon, in fact. But you have a second photon that is emitted, right, at some energy, some angle from the original incidence angle and direction, and there's this electron here, and this electron here now doesn't have a well-defined energy. Why? Because now we have to, for conservation of energy, this plus this must be equal to the incident electron energy, photon energy, and we don't really know how much was each of them. If we know the scattering angle, then okay, we can calculate. It's a simple equation, but we don't usually know. And then we don't usually know how much energy went to the Compton electron, how much went to the scattered photon, right? So that's it. You have a Goldman photon that interact here, the second photon is emitted, and a Compton electron is ejected. Now without a very well-defined energy, right? So if we take a look, this image should make things clear. If we had a photoelectric effect, say we have a photon with Hν energy, the energy will be essentially Hν minus the binding energy of that electron. They would all have the same energy here, right? The electrons. But when we talk about Compton, they fall inside what we call Compton continuum. There's a maximum allowed energy, which we call Compton edge. And why can't we go all the way here? Because of conservation of momentum. Some of the energy must go to the second photon, otherwise you don't conserve energy, right? And so that's how it goes. And if we go here, we can calculate just putting 0 or pi, and you know the two limits, the upper limit and the lower limit. So this is Compton, and this predominates essentially on medium energies, right? We'll see about it later, but this is the predominant interaction when photons have a bit more energy, or when the medium is very light, like hydrogen or something. Then we have pair production. It's not phase, it's pair production. Pair production is when we have one of those strange things that only quantum mechanics can do for you. Now suppose you have a photon with very high energy. Its energy is so big that it can be enough to produce one electron and one positron. If we already know that, remember I told you that 511 kilo electron volts, that was the rest mass of the rest energy mass of the electron, was an important number. Yes, that's why. Because all of a sudden, if your photon has more than twice that, you can produce an electron-positron pair. And why do we need to produce a pair? Particle-antiparticle pair, because the charge must be conserved. So one must be positive and the other is negative. And because that's an essential rule. You can produce a particle-antiparticle pair, or you can, when a particle meets an antiparticle, they can annihilate and release that energy back. But it must be a particle-antiparticle pair. So the antiparticle of the electron is the positron, and they are the lightest particles available. Because yes, if the energy, let's suppose we're talking about giga electron volts, tera electron volts, then yes, you can start producing proton-antiproton pairs and other things like that. Essentially, that's what happens on the atmosphere when we talk about the cosmic rays. They start very high energy gamma rays interact with our atmosphere and start producing all these strange things because it has very, very high energy, much above tera electron volts. Or that's what we do in on very large particle accelerators. That's what we do too, right? We accelerate particles so that we give them so much energy that these processes can start happening. But in the real world, in our ordinary world, that world we go to sleep in, wake up, and okay, we don't have those kinds of energies available usually. So, but we do have some photons that are greater than 1 MeV, 1.022 MeV. So, what we can produce and will produce is pairs. It's electron-positron pairs. So, the incident photon comes and it senses the nuclear field. It requires a nuclear field to do that because someone has to absorb the excess momentum. It's required. So it will enter, it will find a nucleus, but it will not interact with the nucleus itself. It will only feel the nucleus and use its potential to, just like when you get a bottle of very cold water or beer or something, and you just put your hand on it, and all of a sudden it freezes all over. It was there, it was liquid, you just got your hand here or just dropped it, just bumped it into the sink, and it all freezes very instantly. It's essentially the same thing. The nuclear field will do that. So it will get that gamma ray, and all of a sudden, by sensing the nucleus, the photon will transform into electron and an electron and a positron, right? And now we have one electron with some energy, because the excess energy will split between those two in form of kinetic energy. So now we have an electron, which is light ionizing particle that will ionizate the medium the way it is. And here we have a positron, which is another light ionizing particle that will ionizate the medium the way it does. And when in the end of its trajectory, when it's stopping, find an electron and just annihilate again and produce two 511 kilo electron volt gamma rays, right? So pair production is essentially a quantum event in which your photon may become, you get energy to translate into mass instantly. So energy will become an electron plus a positron. The only requirement is that you have a nuclear field and you have more than 1.022 mega electron volts. Right, so that's it. You have if you have less than this energy, it does not happen because you do not have enough energy. But if you have more than 1.02 MeV or 1022 kilo electron volts, it will sense the nucleus and split into one electron and one positron. And the electron will go on ionizing the medium as it does, and the positron will go on ionizing the medium until it stops and annihilates, producing two 511 kilo electron volt gamma rays and annihilating one electron that was in the medium. Here we can have an idea. So as I told you, for high Z and low energy and high Z and low energy, photoelectric effect is the most important one. For average energies, essentially for all parts of for low energy and low Z or for intermediate energies, or for high energies and very low Z, still the Compton scattering prevails. For higher energy, especially for heavier targets, pair production is the one that prevails. Okay, so heavy Z, photoelectric effect, or pair production, depending on the energy. Low energy photoelectric, high energy pair production. Compton scattering, the whole rest. Right? So, and now if we repeated the same thing we did there, we will start putting attenuators here. But now there's one thing. Once one electron interacts with the medium, no matter if it was the gamma rays or photons, they are very easy to identify in energy. So gamma ray detectors, X-ray detectors, once the radiation lost its energy, it's not the same radiation again. It's another radiation that's less penetrant and everything. Maybe I haven't touched this, but higher energy requires more depth to stop. It's also true for gamma radiation, right? And for here, you start to increase the absorber and it starts to drop exponentially, right? So once again, it's an exponential transmission, meaning that if I go 40 centimeters in this case, I will drop a half. At 8 centimeters, I'm at 1/4, and so on and so on, right? There's also photonuclear reactions, as I told you when we were talking nuclear reactions, right? Those gamma N and gamma something reactions, right? They start to happen when the photon energy is greater than the separation energy for a single nucleon, because it's the simplest thing you can do. Just take one nucleon away, right? And that requires quite much more energy than it usually happens, only above 2 megaelectron volts or something, 2 MeV, right? And when we start to think about nuclear reactions, because all these interactions we said so far, the light, the heavy charged particles, the light charged particles, they were interacting with the electrons or with the nuclear field, not with the nucleus itself. So the nucleus was not left, the nucleus does not change. So there's no residual radiation, right? If anything, you may have X-rays, but they're immediate, they're not delayed. When we talk about gamma rays, we talk about photoelectric effect, or we talk about, we're not talking anything radioactive. You're not changing the nucleus, so nucleus will not become radioactive. If you happen to have a photonuclear reaction, that's no longer true. You may take a stable nucleus and change it into a radioactive nucleus. That's why when we talk about applications, you'll see that at some point I say, okay, you can irradiate things. We irradiate food, we irradiate rubber and all that with gamma radiation. And we are not afraid that things will become radioactive, because energies are calculated to be well below the threshold for photonuclear reactions, right? If a photonuclear reaction happens, then you can have a radioactive nucleus as the remains of it. Okay. Well, as I just said, for gamma radiation, as the absorption follows an exponential rule, right? There is such a thing as what we call half thickness, which is the thickness at which the intensity gets down to half of it. And just like with the decays and every other exponential decay thing, this will be true, and all the relations will be the same. Okay, I'm not really concerned that you have this in your mind, but just remember that you will not block all of gamma radiation ever. You can really reduce its intensity, but it will take, if it takes 1 centimeter to take it by half, takes 2 centimeters to reduce it by 2 1/4, and it will take you 3 centimeters to reduce it to 1/8, and so goes, right? So at some point you have to stop and say, okay, that's enough for me. And essentially that's it. So let's remember the basic facts about when we're talking about this radiation. For all kinds of interactions, the higher the Z, the stronger the interaction, right? This is something very important, because this means that if you want to shield yourself from gamma rays, I made it clear for a photoelectric effect, not that much for quantum, but it's also true. Higher the Z, the stronger it is. Meaning that essentially, if you want to shield yourself from gamma rays, you need high Z materials. Meaning lead. That's why you see so much lead being used as shielding. Because when we think alpha particles, they travel, as I told you, some centimeters in the air and a few micrometers in matter. So anything shields it, in fact. When it's all beta radiation, we're thinking about some meters in the air, or some half a centimeter or a centimeter in matter. So you have light matter, anything, it's not important. You use polyethylene, you use acrylic, or you use wood, and it's okay. Now, when we're talking electromagnetic radiation, that's a different thing. We need high Z materials. But on the other hand, it just goes away. It has, for instance, just some information I have in my mind or something. If you have like 1 centimeter of lead, you will, for 600 kilo electron volts or something, you will reduce the intensity to 1/4 of it. So it's not that much. It's large, okay, but not that much. If you want really to disappear, you need 10 centimeters of lead, right, for 600 electron volts, kilo electron volts. If we're talking more energy, we need even more shielding. And that's why, if you take a look at laboratories that deal with radiation, we usually have very large lead shields, right? Because the other radiations are easy to shield. The hard one is the photoelectric one, is the gamma rays, and it's not any material. It's high Z materials. So we're talking 10 centimeters of lead, right? Sometimes even more. We're talking, for instance, in extreme cases, there are shieldings that employ, because when we talk lead, we're talking Z equal to 82. If we talk uranium, Z is equal to 92. So it's way bigger. So if you want a really, really efficient shield that fits in a shorter space, you can make shielding with uranium. Yes, I know uranium is radioactive. Then you have to, usually you have a uranium shield sandwiched into a lead shield. So the lead is only there to block you from the uranium radiation, and the uranium will do the real shielding for high energy gamma rays. It's very expensive, but yes, they do exist. And there's also, for instance, the walls in our reactor. They are not plain concrete, because you could use 2 meters of concrete, 1 meter of concrete, but you do better than that. You get concrete, which is essentially silicon, right? It's silicon and oxygen and a bit of iron, all low Z materials, except iron, a bit larger, and you use a mineral called barite. Barite, yes, barium rich material. Barium has a much larger, if I'm not mistaken, it's 53, the atomic number, so much larger than silicon or iron. And then you use barium inside, amino rich in barium, mixed in the concrete, so that it increases the attenuation. So just going back, when we're talking shielding from gamma rays, we're talking large shields, and we're talking heavy materials like uranium, lead, the most usual one, or barium in the concrete, things like that. Okay, this is very important, and we're talking about at least 10 centimeters, sometimes more, right? So that's it for today. Okay, bye bye.